One other thing I wanted to show here is our loop compensator tool, which is here by clicking on the output filter for one of our rails. This is a simulation tool that we develop and maintain ourselves. It revolves around this PI filter here outside of the module. So we have capacitance that is closer to the module itself, capacitance that is closer to the load that we have, and then in between, if you have any kind of parasitic inductance that either due to the PCB traces or anything else that would be in between the transmission of between the module and the load, that's also modeled here. And there's a few different scenarios you can use this. One thing I will point out here is that this may seem like there's a lot going on, but you can actually also go into a wizard mode, which kind of goes and walks you through the different scenarios in which you could look for control loop stability or optimize for the components. I'm going to kind of go back here and stick around in the full view. So one thing you could do, one scenario is if you already had components that you wanted to optimize for using appropriately, like say you had a bunch of 470 mic caps in inventory and to the point where they're actually cheaper than using 100 mic caps, you could actually optimize your design for that. You can actually assign kind of cost weighting for the different capacitors that you have in here as well. So that's one use case. A more common one is for optimizing the control loop. So when you set control loop parameters and you optimize here, this is going to impact what we call like the PID coefficients that operate in our part. Now you might be thinking, well, a lot of our parts do offer dynamic loop compensation, which is something kind of built into the module itself. That works in a lot of cases. Now there are scenarios though where you may have really tight requirements and you may want the control loop parameters to be optimized, but also you may want a static expected response every time. That's where this tool comes in. So for instance, one other thing I'm going to show here. First, we have a loop response here, and we can also see our transient response. It doesn't look that great right now. It's kind of not quite meeting our requirements. And again, those requirements are defined down here in the load transient. Here you define the load step, and you can then find the requirements down below here. So this is our load transient response requirements right now. There's a few ways we can optimize this. One is we can optimize for what's called a robust response, and that basically means that it's going to create a set of parameters that is, it's not the most optimal for transient response, but it's going to be a bit better at handling component variances. Let's try this at first, and one thing I will also show here is you get all the raw numbers of your system here too, the calculated gain and phase margins down here as well. So, and those will get updated as we go through these optimization routines. So let me first try robust here. So we got some improvement. We have less ringing, but we're not quite meeting our requirements for the peak-to-peak here. So let's go ahead and try the optimize button here, and it looks like I had already gone through and optimized this here, so we're going to go ahead and click use this, apply the solution. Let's see, we're still not quite meeting our load transient requirements, and if we go up here we can see meeting it, we're at 3 times more than what our deviation should be. So let's try to then change our output capacitor situation here. And we really don't have much here, so let's increase these 470 mic here, and let's add the number and change that to 10. And I'm also going to decrease the ESR here. Change it to 5. And then I'm going to also increase the number of 100 mic caps here. Of course, now we changed the model here of the pi filter, we want to re-optimize again, so I'll go ahead and click this, and it's going to go through, and it'll update our simulation, and now it's showing us a green light, showing us meeting the requirements. And just to show our results here for the phase margin, it looks like things are improved a bit here as well. Just to show a few other little things, we can also see output ripple here. If I click here, see the output ripple deviation, ramp up, down, as well as things like output impedance, which may be important for other scenarios.